I would like to begin saying hello to everybody, to the organizers, to the speakers, to the participants, and especially to the participants, because you know, in a meeting, the participants are extremely important, because when there is no participants, there is no meeting. Okay, so I am sorry that we cannot be together in the same classroom in Bangalore, but that's life. We have to adapt. And I will try to give the lecture in this setting, which is not very familiar for me. Okay, I hope I will succeed. Okay, second very important thing, I would like to thank the organizers, the ICTS, for the, okay, first for inviting me to give this series of lessons, and also for the good organization and the work of organization. I know that organizing a meeting is something which is very time consuming. Okay, I will present a work. Okay, I would like to pass to the second transparency. Okay, I will present a work which will be a work in collaboration with Antonio Gaudiello and Olivier Guibet. So you know both of them. Antonio, because he is my chairman now, and Olivier, because he was the previous speaker. So what I will describe is an example of bounded homogenization, and which will be the homogenization of the Neumann brush problem. Okay, I will, of course, explain exactly what I mean by that. Okay, this work is based on two papers. One, okay, so those are two papers by Antonio, Olivier, and myself. The first one is published in Archive for Rational Mechanics and Analysis, and it was published already in 2017. Okay. And is concerned with the homogenization of the brush problem, that's good, with a source term in L1. Okay, so this is a mixing of renormalized solution for right-hand side in L1 and homogenization of the brush problem. But in this paper, there is a section which describes the case where the source term is not in L1, but in L2, and this is what I will describe now. Okay, this second paper is to appear. Okay, who knows when? Okay, I hope soon, because okay, all the work is done, but this is a problem of writing the things in the more clear way possible. And this is a case where the density of the teeth can vanish. Okay, so you will understand what I mean later. Okay, the contents will be the following. Okay. Okay, first of all, I should say that I will teach that not like a seminar, but like a course. So I will be slow. I will try to be precise on everything and to prove almost everything. Okay. Okay, I will begin with some notation. Then I will give the position of the problem. And in particular, I will describe the geometries of omega and of the brush omega epsilon. So this is the more specific part of the paper. Then I will give the statements of the homogenization and corrector result. And then I will pass to the proof of the homogenization theorem and to the proof of the corrector theorem. And finally, but I think I will not have the time to do that, I will, in some appendix, prove to some properties, the most interesting properties being a property of density, that the fact that H1 of omega is dense in some strange space V of omega. Okay, let me begin with the notation. Okay, the notation are basic, but I would like to emphasize some point. I will work in Rn with n more than 2. Okay, epsilon will be a sequence which tends to 0 of real number, strictly decreasing. Okay, every point x in Rn will be decomposed in 2 parts. The first part, x prime, which is the first n-1 components, and the second part, xn, which is the last coordinate, the vertical coordinate. Omega will always be open and bounded and included in Rn. D will denote the gradient. Okay, so again, it will be divided in 2 parts. The n-1 first partial derivative, and the last vertical derivative. Okay, now I will use a space that everybody here should know. Okay, I hope. And this space is each one of omega. Okay, but I would like to emphasize clearly the definition of each one, because it will play a role in what follows. This will be the set of all function V, which are function in L2 of omega. Okay, actually those are classes of function, but I will speak about functions, such that the derivative of V in the sense of distributions in omega is in L2 of omega to the power n. So, okay, I repeat the definition. The function in L2, such that the definition, the derivative, the gradient in the sense of distribution belongs to L2 of Rn. L2 of omega to the power n. In particular, omega is not assumed to be smooth. And there is, for example, the function of, there is no extension property of omega to Rn, which is assumed. And this will play a role. Okay, I will use another space, which is similar to each one, less known, but very common nevertheless, which is a space each of omega dxn, the vertical derivative, which is the space of the function in L2 of omega, such that the vertical derivative of V in the sense of distribution belongs to L2. Okay, they are endowed with the natural norms, and with the natural norms, they are Hilbert spaces. Okay, another important notation will be that omega will be divided in 2 parts, omega A and omega b, and A stands for above, while B stands for below. Okay, so the notation, I hope, is clear. A last notation, if I have a function VA epsilon, which is defined in a set omega A epsilon, okay, where omega A epsilon is included in omega. Okay, I will write that here. Okay, so if I have a function defined in omega A epsilon, I will define its extension V epsilon A twiddle by 0 to omega A by setting VA epsilon twiddle equals VA epsilon in omega A epsilon and 0 in omega A minus omega A epsilon. So if VA epsilon is in L1 of omega A epsilon, then VA epsilon twiddle is in L1 of omega. Okay, and now I can explain what is the problem which is of interest for us. Okay, café. Okay, the position of the problem is the following. I am looking for U epsilon, which is the solution of a Neumann problem. Okay, so Neumann boundary condition. The problem is a problem minus divergence of A of x gradient U epsilon plus C of x U epsilon equals F of x in omega epsilon. Okay, so this operator here is a second order operator, okay, of the type of the Laplacian, but with L infinity coefficient. So A of x will be a L infinity matrix which is coercive. Then there is, okay, so this is a generalization of minus delta. C of x will be a coefficient bounded in L2 and bounded from below by a strictly positive constant. So you can think about C of x equals 1, and F will be in L2. And the equation takes place in a set omega epsilon was, and I denote by n epsilon, the exterior normal to d omega epsilon. This is in the case where omega epsilon is smooth. Actually, it will not be smooth, but okay, this. And the boundary condition is a Neumann boundary condition. So A of x du epsilon n epsilon of x equals 0 on the omega epsilon. In the case of the Laplace operator, all of that is minus delta U epsilon plus U epsilon equals F, and du epsilon over dn equals 0 on d omega epsilon. Okay, so okay, we will make hypothesis which allows one to have a unique solution to this problem. And what we want to do, assuming that omega epsilon is included in omega and that omega epsilon tends to omega in a certain sense that I will describe, we want to pass to the limit as epsilon tends to 0, and I will call that homogenization, and to provide an explicit representation of U epsilon and of its gradient, a result that I will call corrector. Okay, so let me describe now, okay, what I will call the data, which says A of x, C of x, and F of x. Okay, so those data, first of all, okay, recall that omega epsilon is included in omega. Omega is a fixed set, and omega epsilon is a set with an oscillating boundary, which will converge in some sense to omega. And the data are defined of the whole of omega and not only on omega epsilon. A of x will be an n by n coercive matrix with bounded coefficients. So a matrix in L infinity of omega n by n, such that, which is coercive, in the sense that A of x lambda lambda is greater than alpha lambda square for a given alpha strictly positive, almost everywhere in x in omega, and for every lambda in Rn. So this is a classical coercive matrix with coefficient in L infinity, which is a generalization of the identity. C of x is in L infinity, and C of x is in some sense also coercive, in the sense that it is greater than some gamma, and this gamma is strictly positive. And finally, f of x is in L2. So the case where f of x is in L1 can be considered, and this is exactly what we did in our first paper with Olivier and Antonio. And so in this case, we have to mix what Olivier is describing with what I will describe in those three lessons. Okay, but I will not do that today. Today I will consider the case, classical case f in L2, just because if you don't understand the case f in L2, you cannot understand the case f in L1. Okay, so I told you that I will be interested by this problem, this partial differential equation with a boundary condition of Neumann. But actually, what I will consider is exactly this problem, but in the variational sense. So I will not be interested in the partial differential equation, and the meaning of the partial differential equation, the meaning of the boundary condition. I will use the variational formulation, which is to say that I will look for some u epsilon which belongs to each one of omega epsilon. Remember that omega epsilon is open. Okay, so this is defined, this space is defined, such that for every v epsilon in each one of omega epsilon, we have the following equality: the integral over omega epsilon of A gradient u epsilon gradient v epsilon plus the integral over omega epsilon of C u epsilon v epsilon is equal to f v epsilon. Okay, and this is classically called the variational formulation of the problem. This is what I will use. I will not use actually this formulation, which is not a mathematical correct formulation, because I didn't say what does this mean that the equation takes place in omega epsilon, and neither the sense of this boundary condition here, but we know that if omega epsilon is sufficiently smooth, then the solution of this problem is a solution of the equation, the partial differential equation with boundary Neumann condition. And conversely, if u epsilon is sufficiently smooth and satisfy this formulation, then it is a solution of the variational formulation. Okay, good. So I pass to that, we will return to that. And now I have, okay, remember that we are interested in the partial differential equation in omega epsilon. What is omega epsilon? What is omega? So here you have a picture, okay, due to Olivier Guibet. Thank you, Olivier, for your work. And this picture is in 2 dimensions here, or in 3 dimensions here. Okay. And I will describe first what is omega. Omega is here. And what is omega epsilon? Omega epsilon is here. Okay. So I will describe that in all details. Okay, I will tell you that omega epsilon will be a comb if n is equal to 2, and a brush if n is equal to 3. So I have the comb. No, okay, I have no comb and I have no brush, so no problem. Okay, omega epsilon will be a comb. You have this example, or a brush, this example. And in this story, omega epsilon is made of a fixed basis omega b. B is for below, but also for basis, and is fixed for every epsilon. And on this basis, there are these omega a epsilon, which are distributed, okay, and a here is for above. Okay, so, and I will, for every n more than or equal to 2, I will call omega epsilon a brush, even if in dimension 2, this is really a comb. And omega a epsilon will be the teeth. Okay? What is omega? Omega is here. And I explain how it is done. So this is n equals 2. This is n equals 3. But once you understand how the case of dimension 2, you have understood everything. Okay, definition of omega. I take omega prime, which is a subset of Rn minus 1. Okay, this is why I assume that n is more than 2. Okay, and omega prime is open and bounded, but has no regularity on the boundary. Okay, and omega prime will be the cross section of my omega. Okay, so this is a subset, an open subset of Rn minus 1. Then I have 3 functions, psi-a, psi0, and psi-b, which is defined on Rn minus 1. Psi-a is a continuous function, psi-b is a continuous function, and psi0 is a Lipschitz function. Okay, and here are the 3 functions, and there exists some eta strictly positive, such that psi-b plus eta is less than psi0, and which is less than psi-a minus eta. So this means that psi-a, psi0, and psi-b are separated. And here is a picture, and you have the graphs of psi-a, the graph of psi0, and the graph of psi-b. Okay? And now I will introduce the almost the last notation, I will introduce omega A, sigma A, omega B, sigma B, and sigma 0. Okay. What are what are sigma A, sigma 0, and sigma B? Sigma A is the graph of psi A of x in omega prime. Sigma 0 is the graph of psi 0 in omega prime, and sigma B is the graph of psi B in omega prime. This is written here. Okay, for example, sigma A is is made of the point x prime xn with xn equals psi prime of x prime, psi A of x prime, and x prime is in omega prime. Okay? Psi 0, same definition, and psi B, psi B, same definition. Now I define omega A as the, okay, I begin with omega B. I define omega B with the set of, which is between, which is a cylinder, a vertical cylinder, with a basis which is sigma, okay, a below boundary which is sigma B, and an above boundary which is sigma 0. So this is the set of the xn such that x prime belongs to omega prime and psi xn is between psi b and psi 0, and this is strictly less, so this is an open set. Okay, omega A is the above part of omega, and it is here. This is a vertical cylinder with above boundary which is sigma A and a below boundary which is sigma 0. So in this way, I have defined sigma A, sigma 0, sigma B, omega A, omega B, and omega will be the union of omega A, of sigma 0, and of omega B. So the set of the set of the point in Rn such that x prime is in omega prime, and the set where xn is between psi b and psi a. So this is this set here. Okay, let me go back to the picture which is here. In this picture, we see clearly omega in dimension 2. We see that omega is a cylinder. Omega A also is a cylinder. Omega B is a cylinder. Omega is all of that. Here, the lateral boundary are vertical, and there is an interface between sigma 0 between omega A and omega B, and to the bottom boundary and the above boundary, sigma A, B, and sigma A. Okay, this is the same thing in dimension 3 or in dimension n in general. Okay, so omega is described. Let me make very few remarks. So the remark is that omega A, and omega B are open sets with above and below boundaries. If we make the change of variables which to x prime xn in Rn gives y prime yn defined by y prime prime equals x prime, yn equals xn minus psi 0, we transform the we transform psi 0 in the hyperplane xn equals 0. Okay, so, and this change of variable is a bijection, which is Lipschitz in the two senses. So you don't modify in this way the definition of each one. Okay, now the definition of the brush, omega epsilon, and of the density of the teeth in omega A. Okay, I would like to have the picture. So the picture will be like that. This will be my model, and I will explain how it is done. And more exactly, I will describe the teeth. Okay, so omega epsilon will be done by the basis omega b, which we had below, which will be fixed for every epsilon. Okay, and on this basis, I will put teeth, which are cylinders, those cylinders are between sigma A and sigma 0. Okay, so there are many of those small cylinders, and I will describe those small cylinders that I will call a tooth. And so the in plural, the teeth. Okay, for that, I will describe the tooth. Any tooth will be a cylinder, so I will describe its cross-section. The cross-section of one tooth for epsilon given, okay, and G given will be a set omega prime J epsilon, okay. Epsilon because we are at the epsilon size, and J is an index, and this index varies in a set G epsilon, which depends on epsilon, which is a finite or countable set of indices. Think about a finite set of indices. Okay, each cross-section here is a subset of Rn minus 1, okay, which is open, connected, and bounded. And there are, okay, the cross-sections are not smooth, absolutely no hypothesis of smoothness except open and connected, okay, and bounded, okay. And there are two more conditions. The conditions are that every omega omega prime J epsilon has a small diameter, and more exactly that for every J in J epsilon, so epsilon fixed, the diameter of the cross-section is less than epsilon, okay? And this is the first condition. So those are small sets, small cross-section. So the cylinder will have a small diameter, okay? And the second condition is that omega, for every k and which is different of L, with k and L in the set of indices G epsilon, the omega epsilon k and omega epsilon L have an empty intersection. Okay, so this means that the sets omega epsilon k and omega epsilon L are disjoint, but be careful. Omega epsilon j, the omega epsilon j are open, so they are disjoint as open set, but it is quite possible that their closure is not empty. So that means that they share part of their boundaries, or they are adjacent. And I will give an example. Here, let me look at that. Here you have a teeth. Okay, so the teeth, this is the tooth is a cylinder, vertical cylinder between sigma A and sigma 0. Okay, the diameter is less than or equal to epsilon, and the basis is not specially smooth. Okay, of course, in dimension 2, this is an interval, so it's smooth, but it is not the case in dimension 3. But, okay, but if the tooths are disjoint, but you can see that, for example, here, in this area, we have 3 different tooths, 3 different teeth, and they are disjoint, but they are adjacent in the sense that they share the same vertical boundaries. Okay? So no regularity. Okay, the teeth are disjoint, the cross-section are not smooth, and they can have, the tooth can be adjacent, so have a common part of the boundary. Okay, let me now define the density theta of the teeth. I will assume that the characteristic function of omega epsilon prime, which is the union of the cross-section of the teeth. Okay, I will denote the characteristic function by key, omega epsilon, and not as Olivier did it, by 1 omega, okay, sorry, 1 omega prime epsilon. So this is the notation of Olivier. This is my notation, but they are the same thing. Okay, so the characteristic function of the union of the cross-section of the teeth. Okay, those are characteristic function of open set. So this characteristic function is in L infinity of Rn minus 1, and I assume that there exists some theta, which is a function in L infinity of Rn minus 1, such that the characteristic function converge weakly star in L infinity to theta. Okay, with naturally theta between 0 and 1 almost everywhere in Rn minus 1. Okay, this is a free of charge assumption because I can always extract a subsequence epsilon prime such that this works for some theta with theta between 0 and 1. And now I make a real assumption. The real assumption is that I assume that there exists a theta 0 strictly positive such that theta of x prime is always more than theta 0, always in Rn minus 1. Okay? Okay, what is theta? Actually, theta is the density of the homogeneities in omega A. So the souvenir, the reminder of what was the omega epsilon. At the end, the teeth are more and more numerous. There are more and more teeth, but they are smaller and smaller because epsilon tends to 0. And due to that, at the limit, there is not a picture like that, where every teeth is characterized, but a density in the set omega epsilon at the limit. So, and this density is theta, which is between 0 and 1. Okay, but here in these lessons, I will assume that there is always a strictly positive density of matter, and more exactly that this density is more than a fixed theta 0 strictly positive. So there are teeth, okay, not everywhere, but there is a positive density of matter in omega A. Okay, note that the case, of course, which is more interesting, is the case where theta 0 is 0, and this is the thing that we have solved in the case, in the paper to appear with Olivier and Antonio, but this needs some more effort, and if you don't understand the case theta 0 strictly positive, you cannot understand, in my opinion, the case theta 0 equals 0. Okay, so here is a general picture of the situation. Omega in dimension 2, omega okay, I forgot to say something. Okay, I will say it in 1 minute. Omega epsilon, and here this is the same picture in dimension 3. But if you remember what happens in dimension 2, you have understood everything. Okay, I forget to say something. And something is the definition of omega A epsilon. So we add the cross-section of each tooth. Omega epsilon prime is the union of the cross-section. Okay, the union of the cross-section of the teeth for epsilon fixed. I define now omega epsilon in the following way. I take Q epsilon, the forest of vertical cylinder with cross-section omega prime epsilon and infinite length. So I put a cylinder on each cross-section omega prime j epsilon. I put an infinite cylinder omega prime j epsilon times r, a vertical infinite cylinder, and Q epsilon is the union of those cylinders. Okay, and then I can define two things: omega A epsilon, which is the intersection of this forest of cylinders with omega A, and sigma 0 epsilon, which is the intersection of this forest of cylinders with the boundary sigma 0. And omega epsilon will be made by gluing omega A epsilon and omega B by the intermediate boundary sigma epsilon 0. So in other words, so this is omega B, which is fixed. Okay, this is omega. Okay, the part which is in gray is the okay, more exactly, this is the part which is in gray in this area is omega A epsilon, and sigma epsilon is the gluing between the two things. Okay? So now we know what is omega, we know what it is omega A, omega B, and we know what is omega epsilon, omega A epsilon, sigma epsilon 0, and omega B. Okay, and of course, omega epsilon is included in omega, and so we can pass to the statement of our results. Okay, so in principle, Antonio, I should stop now, I guess, because I'm at the end of my time. But okay, if you don't mind, I will just go a little bit further by giving not the statement of the theorem, but what will be the homogenized problem. So what we want to do.
François, excuse me, just a moment, we see if there are some questions, otherwise you can continue. Some question, some remark?
Very good. So, okay, give 1 minute to people to decide if they want to have some question, and to me to have some coffee.
No, we have a question. It seems that you can go on for 5 minutes, okay?
Thank you, Mr. Chairman. So I will begin with the statement of the homogenization and corrector result. And okay, I say again what I want to do. I want to pass to the limit in this partial differential equation, which is with Neumann boundary condition, which is posed in omega epsilon, and omega epsilon is a brush as described before. So I have some omega epsilon, which is included in omega, and this omega epsilon is a brush, and epsilon tends to 0. Okay? More exactly, what I want to do is not to pass to the limit in this problem, but as I said before, in the variational formulation, which is here, which is a problem which is well posed, because this problem has a unique solution U epsilon, okay, has a solution U epsilon, and this solution is unique, okay? So this is Lax-Milgram lemma, so no doubt that this is correctly defined when the matrix A is L infinity, is a matrix with L infinity coefficient, which is coercive, with alpha strictly positive, and when C is a coefficient in L infinity more than gamma, with gamma strictly positive. And here, as I said, omega is omega A union the intermediate boundary sigma 0 union omega B. Omega A and omega B are open sets, and the brush omega epsilon is also the union of omega A epsilon, the intermediate gluing boundary, and omega B. Okay, and I want to let epsilon tend to 0. Okay.
François?
Yes.
There is a question. If you can read on the chat.
Yeah, but this is not very okay. I think I cannot with the tablet. I cannot. So,
okay. Do you have some other application in mind, excepting the brush or the comb?
Okay. I have no application in mind. Okay, to be precise. Okay, of course. Okay, I explain what I mean. You Okay, the notation brush or comb is just a notation for the geometry, okay? Because we do not are hairdressers, and we will not use the equation of the comb and the equation of the brush to hairdress, okay? But there are many cases where you have forms which looks like that. For example, radiators, when you have a lot of things which have exactly the form of a brush, in which you have something which is either cold or hot. Cold when you want to make the medium outside to be cooled, or hot when you want to heat the exterior medium. Unfortunately, for this type of things, this is not the Neumann boundary condition, because for the transmission of the heat, you need that the heat goes out of the omega epsilon. And in this case, this is precisely the contrary. There is no flux. The Neumann boundary condition says that there is no flux through the boundary. So this equation is not the equation of a radiator. Okay. So you can imagine things, for example, a membrane between two chemical reactants or things like that. But basically, what I do here, this is, okay, I don't know any real physical problem which is modeled, okay, with that, and which has a physical interest, okay? Because exactly, the Neumann condition is exactly not the radiator, is the contrary of a radiator. Is that clear?
There are another
Question?
To Maria Neusradu. There is another question, Irina Peterson. Dear François, why do you have different regularity assumption on Psi0, Psi-A, and Psi-B? Will be clear later?
Yeah, it will be clear later. Okay, I can explain. We try to have the minimum assumptions. Okay, so no regularity on omega prime, the basis. Okay, omega prime, which is not the basis, but which is a cross section of omega. Let me go back here. Okay, so the omega prime, which is here, has no regularity in n-1. Why do we need the sigma 0 to be Lipschitz? Because we would like that the functions of each one of omega b have a trace on sigma 0. Okay, this will be very important, that the function define. Let me go to this picture, which is better. It will be very important that the function in each one of omega b have a trace on sigma 0, and also that the function in omega a have a trace on sigma 0. And for this reason, we need Psi0 to be Lipschitz. Okay? For sigma A and sigma B, we only need continuity, and this will be transparent for that. Actually, okay, what we want is that omega B and omega A are open sets. So this necessitates, this needs Psi A and Psi B to be continuous.
François?
Yeah.
Just a last question. Allora, is Sheraya Kodalkar She asked, can we apply this theory to moving surface interface?
Maybe we can. We didn't think about that. Okay, recall that this is at the moment a stationary problem. Okay, we are speaking about something which is stationary. We could imagine that there is some time and that the boundaries of the tooth of every teeth is moving. Okay, but okay, maybe we can consider that.
We are over time. Just the last one question. Bensiali, he asked, did you consider other type of boundary condition like Robin wants? Yes, I think it's possible.
Okay. So the lessons are about Neumann boundary condition in this very particular geometry. Okay, the geometry is very particular and the boundary condition is very particular, and this is Neumann. Okay, we are able to treat the case of non-homogeneous Neumann boundary conditions. Okay, if we pass to other boundary conditions, for example, Dirichlet, the result is completely different. Okay, is dramatically completely different. Okay, I will maybe say a few words about that if somebody is interested, but Neumann boundary condition in homogenization is very different of Dirichlet boundary condition, and the results are completely divergent. Okay, Robin is in some sense close to Neumann, except when the coefficient, which is the u epsilon dn plus, sorry, let me write, du epsilon over dn epsilon plus k epsilon u epsilon equals 0, for example, or g epsilon on d omega epsilon, everything depends on the size of k epsilon. Okay, and also on the size of g epsilon, but this is another thing. So let me think about the case where this is 0. If k epsilon is fixed or small, no problem. If k epsilon goes to infinity, you are passing from Neumann to Dirichlet. So this is another problem. So it will be something intermediate where when k epsilon is well chosen, it will be a critical value of k epsilon. If k epsilon is small, you go to k epsilon very small, then, okay, more exactly to a power of epsilon, you go to, this is like Neumann. If k epsilon is much bigger than epsilon to some power, you go to Dirichlet. And in between, you have a critical case. But for that, I suggest everybody to ask the question to Patrizia Donato, who is the master in this story.
Okay, thank you very much, François, for this clear and pedagogical lecture. And we tomorrow for the second lecture.
Thank you. Thank you a lot.